It's my honor to introduce Mayur Naik. He did his PhD at Stanford University. He afterwards worked at Intel, I think, for a time, and then you were at Georgia Tech for a while, and now he's an associate professor at University of Pennsylvania, UPenn. And he's going to tell us about MaxSat and its applications in software verification and in general. Thank you.
Thank you, George. Okay, this is work with several fine folks here that I've listed below. Let me begin with some background. So there are many different approaches to software analysis, which are algorithms for discovering useful facts about programs. And one of the dominant approaches is so-called constraint-based approach. Now, this approach comprises two phases. So in the first phase, called constraint generation, it takes as input the program and produces as output a set of constraints. And in the second phase, we have constraint resolution, which takes as input the constraints that were generated and produces a solution. And this is typically a constraint satisfaction problem or a decision problem that encodes the result of the analysis that we want to perform. Now, there's a long history of constraint-based software analysis, going back to type constraints, which are used for type inference, and then set constraints, and more recently, SAT and SMT constraints. And this approach is popular because it has many benefits, some of which I'll list here. So first is that it allows to separate the specification of your software analysis problem from the implementation. It also allows you to leverage sophisticated off-the-shelf solvers for the second phase of constraint resolution. It also yields natural program specifications. What I mean by that is that these constraints can be generated locally from different parts of the program, but then solved to yield global properties about the program, and so on. Okay? So in the modern era, there are many challenges in software analysis which cause problems for this constraint-based approach. So for example, a dominant problem in automated verification is how can we balance various trade-offs? One of these most important trade-offs is between the accuracy of the result of the analysis, or its precision, versus the cost of the analysis or scalability. Another is how to handle uncertain information and noise. Again, something which is very common in real-world software. For example, what if a human provides an incorrect specification? And finally, we don't often have the complete picture. There can be parts of the program that are missing, and so on. And so we need to reason about these parts in a reasonable way. So an emerging approach to handle these problems is to replace constraint satisfaction by its generalization, which is constraint optimization. And in this world of constraint optimization, all of these problems can be treated as objectives that you want to minimize or maximize. Okay? And you see this paradigm quite often in recent years. There are many applications of constraint optimization problems. There's an entire conference dedicated to it called Constraint Programming. Z3 now supports objective functions and so on. So to better understand a classic constraint optimization problem, let us start with a problem that is sort of the prototypical constraint satisfaction problem, the Boolean satisfiability problem. So the SAT problem takes as input a formula of the form I've shown here. It is a set of clauses, here C1 through C5, over Boolean variables, in this case A through D. And the desired output is an assignment of Boolean values to these variables that satisfies all the clauses in this formula, if such an assignment exists. Okay? Now, a natural optimization extension of this classic constraint satisfaction problem is called the maximum satisfiability problem. And more technically, this particular variant of MaxSat that I'm going to talk about throughout this talk is called the weighted partial MaxSat problem, or WPMS. Okay? So in this problem, we have these so-called hard constraints as before, which are C1 and C2, but it also has so-called soft constraints, C3, C4, and C5. And the desired output now is, as before, an assignment to these Boolean variables, A, B, and C, and D, such that C1 and C2 should be satisfied, so the hard constraint should be satisfied, but the sum of the weights of the satisfied soft constraint should also be maximized, okay? So let us look at an example solution here. A maxset solver might return this assignment where A, B, and C are set to true and D is set to false. And you can see that this assignment indeed satisfies C1 and C2. And it satisfies only C3 and C5, but not C4. And therefore, it gains an objective value of 4 plus 7, which is 11, okay, as opposed to 13. And the reason for this is that it's not possible to satisfy all 5 constraints here simultaneously. And so the maxset solver gives up the constraint with the lowest weight, which is C4. Okay? So what is good and bad about the maxset problem? So first of all, it is expressive for the various applications in software analysis that we were interested in. Okay, in particular, it allows us to encode various soundness conditions in software analyses using the hard constraints, and it allows us to encode the different kinds of objectives that we have via soft constraints. Okay? The second is maxset solvers have been remarkably efficient and continue to improve. Here is some data from the recent maxset competition solvers that have competed in it. In 2014, the largest maxset instance that any solver could solve had 4.1 million clauses, and which has gone on to all the way up to 13.3 million clauses. Now, the number of clauses in a formula is not the right indicator for the complexity of the problem, but nevertheless, this should give you some sense of what is the scale of maxset problems that can be solved using state-of-the-art maxset solvers. Okay. Now, here are the things which are not so good about maxset, the maxset problem for our needs. First is, they do not allow us to concisely specify our problems, and in particular, they lack quantifiers. So here's a problem that I'm going to use throughout this talk. It computes graph reachability in a directed graph. And many problems in software analysis can be encoded as graph reachability problems. So I'm going to use this as a prototypical example throughout the talk. And the way we would like to specify graph reachability is in this concise format with quantifiers here. We have 3 constraints. The first constraint captures the base case, which is that from every node X, we can reach itself. There's a path to itself. The second constraint captures transitivity, which says that if there's a path from X to Y, and there's an edge in the graph from Y to Z, then there's a path from X to Z. Okay. And finally, the third constraint is a soft constraint, which says that we should not derive spurious paths. Okay. So whenever you avoid deriving a path, there's a certain reward that is given, which here is arbitrarily set to 1.5. It can be any positive real number. Now, of course, you cannot give this as input to a maxset solver because it has quantifiers, right? So this is something which is lacking in maxset. And another is there's a lack of a high-level structure in maxset at the propositional level that, as I'll show later in the talk, is necessary if we want to scale to very large maxset instances. And so a key challenge is how do we overcome the limitations of maxset while retaining these benefits? And our solution is to use a logic called Markov logic networks from the AI community that is no more expressive than maxset, but it does give us these benefits of conciseness and a high-level structure that we can exploit. Okay? So what is the semantics of MLNs? I'm going to explain that next with respect to maxset. Okay? So here's the syntax of MLNs. It's fairly similar to that of maxset, except that it has these quantifiers. Okay? So an MLN problem is a set of constraints C, which includes a set of hard constraints H and a set of soft constraints S. Right? And what do these constraints look like? The hard constraints are a disjunction of literals, both positive and negative literals, which I call facts over here. Each of these facts is a relational tuple. So there's a relation name R, and there's a list of arguments A1 through AN, where each argument can either be a variable or a constant. Now, in the special case where all the arguments are constants, we call this a ground fact. Okay? And we're going to look at Markov logic networks as programs themselves, so they'll have inputs and outputs. Okay? So these inputs and outputs will themselves be sets of ground facts. And I'm going to give an example to illustrate all of this shortly. Okay? So here's an example which I just showed that indeed is a Markov logic network according to the syntax. Okay? In the rest of this tutorial, what I'm going to do is use a more familiar notation. So in the domain of software analysis, often these constraints take the form of horn clauses that our solver also exploits. And therefore, I'm going to use this data log-like notation whenever possible. Okay? So what we have here is 4 components. There's a specification of which relations are input relations, in this case, the edge relation, which are output relations, in this case, just the path relation, and then what are the hard constraints and the soft constraints. Okay? So notice that the hard constraints now use this notation from data log, where there's a head and a body, but it is essentially syntactic sugar for this particular form that you saw earlier. So that was about the syntax that we'll use. What about the semantics? Okay? So we have to somehow eliminate these quantifiers to reduce this to a maxset instance. And that process is called grounding. It's a fairly straightforward process. So I'm going to define it using valuation sigma from variables to constants. The semantics of an MLN instance is fairly straightforward. It is defined in terms of the semantics of its subcomponents until the point where you reach each individual constraint. And at that point, what we do is we simply blow up each of these quantified constraints by grounding the quantifiers with all possible valuations to constants. Okay? And beyond that, again, grounding each of these constraints is a fairly straightforward task. We push these valuations to the arguments, and if the argument happens to be a variable, then we convert it to a constant as dictated by the valuation. Otherwise, it remains a constant. Okay? So once you understand grounding, the semantics of an MLN is straightforward. It has 2 steps. The first step is this grounding process, where we substitute all quantifiers by all possible valuations to constants, which gives us a maxset instance. And in the second step, we solve this maxset instance using an off-the-shelf maxset solver. Okay? But there's a catch here. So both of these steps are intractable for the problems that we are going to look at. And in particular, we can have up to 10 to the power 30 clauses, which are certainly something that neither of these 2 steps can scale to. Okay? And so I'm going to present a solver that we have developed over the years, which can scale to such instances using an iterative lazy refinement process. Okay? So now to show you one example of how we can solve an MLN. So here's the same problem that I showed earlier for computing graph reachability. Recall that this is a program which has its own input and output. So the input here could be a certain edge relation encoding a certain directed graph. And because we are interested in the domain of software analysis, what we are doing here is encoding an input program, say a Java or a C program, itself as some kind of a graph, okay, in a relational format. And it is being fed to this particular program, which is now, you can think of it as a software analysis. And what we get out of it is this 2-step process. In the first step, we ground these constraints, and you can see that indeed we have replaced all of these quantifiers, x, y, and z, with constants from 1 through 8, which you see in this graph. And now we get this maxset instance, where each Boolean variable is denoted by the corresponding grounded fact. Okay? And a maxset solver could return this as a possible solution, which indeed encodes the set of all valid paths in this graph. Okay? So for example, if the Boolean variable path 1, 1 is set to true, it means that there's indeed a path from node 1 to itself in the solution. And likewise, if path 2, 1 is set to false, it means there's no path from node 2 to node 1. Okay? So before I move on to the rest of the talk, here's the landscape of problems that one can look at in Markov logic networks. So there are inference problems and there are learning problems. The inference problem that we will look at are map inference. And this problem seeks the most likely word, which I just showed using MaxSat. Okay, so we are computing the path relation as the most likely relation. But there's also another inference problem called marginal inference, which I can illustrate using this example. So marginal inference is interested in computing the probability of each of the Boolean variables. Okay? So what is the probability that there's a path from node 2 to node 1 in this graph? Okay? On the learning side, there are also two interesting problems. Where do these weights come from in the real world? Right? And so there is algorithms for learning these weights from training data. And then there's also structure learning, which is where do these constraints come from? And this can be viewed as a program synthesis problem. Now, in this talk, I'm only going to focus on the map inference problem, although we are working on the other three problems as well in various settings. Okay. So here's the outline for the rest of the talk. It will have mainly two technical parts. In the first part, I'll talk about interesting applications in software analysis that were motivated by constraint optimization in general and MaxSat in particular. And then I'm going to talk about techniques that will enable us to solve these applications on real-world code. Okay. I should also mention here that many others have applied MaxSat for various other problems, both in program reasoning and beyond, that I won't be discussing, but we have discussed this in our paper in the proceedings. Okay. Here we'll only focus on the applications that we have developed. Okay, so our central theme is that you should be able to write your software analysis task in the traditional way, using only hard constraints, the way you would write it in the world of constraint satisfaction. Okay? So I've shown you here a datalog program which computes graph reachability. There are no soft constraints here because of the implicit least fixed point semantics of datalog that enforces the same sensible path relation as output. But given such an analysis, what we would like to do is automatically synthesize these different use cases or applications that commonly recur for users of software analysis. So what are these applications? One is a classic problem in automated verification called abstraction selection. So how do you find a good abstraction of a program that you wish to verify? Another occurs in the domain of bug finding, which is how can we accurately classify true positives versus false positives. And finally, more recently, we have worked on interactive verification, which is how can we integrate a human in the loop and ask questions that minimize the user effort in a manner that generalizes well to resolving most alarms. Okay. So in this part of the talk, I'm going to talk about each of these three applications, and I'll show you some common themes across them. I'm going to mainly focus on the first application to go in great detail, but then I'll talk about similar trends in the other two applications as well. Okay. So let us look at a very common kind of program analysis for imperative programs called pointer analysis. So what we have here is a program with two functions, f and g, that have 6 global variables, v1 through v6. Okay, and there are 2 helper functions, id1 and id2, that simply return the argument. You can see that this assertion labeled q2 is indeed valid. On every run of this program, it is indeed the case that at this program point, v1 and v6 can never alias. And the reason for that is v1 and v6 are always allocated at different allocation sites in the program. So they will never refer to the same object. On the other hand, the assertion Q1 is invalid. In fact, it fails on every run because V1 is indeed equal to V3. Okay, so these are in fact called must aliases. And the reason is that V3 gets the value of V2, which in turn gets the value of V1, which is allocated here. Okay? Now, how would we automatically prove this assertion and show that that assertion cannot be proven? Well, a program analysis writer might do the following. So she might use a standard textbook abstraction, which is called 0 CFA. And I'm going to represent it using this particular graph here. Now, what does this graph denote? So the nodes 1, 2, and 3 correspond to the assignments to V1, V2, and V3 that you see here. And nodes 4, 5, and 6 similarly represent the assignments to V4, V5, and V6. Okay? So this graph represents the flow of data between these variables. Now, what you see at nodes 7 and 8 is the flow of data at the calls and returns of ID1 and ID2. So 7 represents the flow of data in ID1 because it is called from both F and G. We have edges incoming into it from 1 and 4. And similarly, node 8 represents the flow of information in ID2. And so we have edges coming in from 2 and 5. Okay. It is easy to see that if you were able to prove that there's no path from node 1 to 6 in this graph, then indeed this assertion is valid in the original program. And likewise, if you can prove that there's no path from node 1 to 3, then that other assertion holds. Okay. Now, the analysis writer might actually express this particular graph reachability problem using the same example I showed earlier in Datalog, using just these two rules. Now, let's see what happens when a user runs this analysis. Okay. So we start out with basic facts, such as that there's a path from node 1 to itself, and then we keep applying these rules until we cannot derive any more tuples, and we have computed the least fixed point of these constraints. So what we see at this point is that we have derived paths from node 1 to 3 as well as from 1 to 6. Okay? So what this means is we have failed to prove both of these assertions. If you can derive a path in this graph, that means you failed to prove the corresponding assertion. But notice that this is a false alarm. We should have been able to prove the assertion that V6 is not equal to V1, right? It's just that we used an imprecise abstraction here. And this is a fundamental problem in software analysis because of the undecidability of aliasing and any other non-trivial program property that you might be interested in. Well, you might use a more precise abstraction here, which is you might want to inline the functions ID1 and ID2 at their call sites. And so now you would get this new graph where I've basically cloned the nodes 7 and 8 for each of the call sites of ID1 and ID2. And at this point, we see a very different derivation. And what we get in the end is only one bug report, which is indeed a bug. In particular, this assertion fails, right? But we have proven the other assertion using this abstraction. Okay, in a realistic program, even though here you're only seeing 4 call sites, in a realistic program, you can have tens of thousands of these. And certainly inlining everything cannot work because it will result in an exponential blow-up in the size of the program, even in the absence of recursion. And so a classic approach to address this problem is the CIGAR approach, or abstraction refinement. And I'm going to show you how we have achieved abstraction refinement using MaxSat for arbitrary analyses written in Datalog. Okay? So a key idea is as follows. So we simply change the rules slightly here to encode a family of abstractions. So I'm going to have one more input here, which dictates what abstraction in this family we are using. Okay? And now you're allowed to use only those edges in computing paths whose labels are enabled by that abstraction. So notice that I've labeled each of these edges. Okay? So we have 16 abstractions in total that are meaningful, okay? And what are these abstractions? For each of A, B, C, and D, we have to make a choice of whether to inline the corresponding ID function or not at the corresponding site. So for example, A0 versus A1 controls the inlining decision of the call to ID1 in the function f, okay? And of course, not inlining is better for scalability, but bad for accuracy, right? So we have to strike this trade-off between precision and scalability. And here's the final result we'd like. So we'd like to say that it was impossible to prove assertion Q1 using any of these 16 abstractions. And furthermore, we were able to prove the assertion Q2 using this minimal abstraction. What I mean by minimal is the number of sites where I've inlined is the least, okay? Now, even though I'm just looking at a finite number of abstractions here, only 16, in practice, we can even have infinite families of abstraction. We would just lose guarantees of termination there. And in practice, you cannot enumerate each of these abstractions in order of cost, because as I mentioned, we are looking at a very large space of abstractions. As opposed to 4 sites here, which induce 16 abstractions, we are in practice looking at up to 50,000 sites, which give you a search space of 2 to the power 50,000. Okay? And so clearly, we need more efficient symbolic techniques to search for good abstractions. Okay? So here's how our cigar approach works. So in the first iteration, we start with the cheapest possible abstraction, which is 0 CFA. And it does not inline any function at any of the call sites. And as expected, we fail to prove both of these assertions. But now let's see how we can generalize this failure so that we don't keep trying each of these 16 abstractions one at a time. What we notice looking at this derivation hypergraph that we obtained from a data log solver is that log. which indicates the fact that we want to penalize whenever there's inlining that's happening. There are other constraints I'm not showing you here, such as the XORs, which is you have to choose between A0 and A1, and likewise between B0 and B1, and so on. A peculiar thing here is that we are even making the provability of assertions as soft constraints, okay? You might think that, well, we don't want to derive a path from 1 to 3, and so we should make it a hard constraint, and likewise for the path from 1 to 6. But keep in mind that certain assertions might indeed be false, like the one here, and more importantly, they might not be provable using any of the assertions in the family of, using any of the abstractions in the family of abstractions that we have. So we need to allow these themselves to be soft constraints. But we assign a much higher weight here, in particular larger than the sum of these rewards, so that if a max set solver comes back with a solution that sets this path to true and thereby gives up a very large reward, then we indeed know that it tried all possible ways to salvage this assertion and prove it, but failed. Okay, so we have a nice completeness result that this assertion cannot be proven using any abstraction in this family of 16 abstractions. Okay. So when we feed this instance to a max set solver, what we get next is the following solution, which amounts to suggesting the following abstraction to try next. And as you can see, it has avoided inlining at sites B, C, and D, and it's only inlining at one site, which is A. Okay, so now we can see the cigar loop here. What happens in each iteration is the data log solver gives a derivation that encodes all abstract counter examples to the max set solver. The max set solver solves a set of constraints and gives back a new abstraction to try. In the second iteration, we get another derivation, which is fed to the max set solver. And this time, we make even more progress. So by just trying 2 abstractions, we have eliminated 8 abstractions for Q1 and 5 abstractions for Q2. Okay? The next abstraction the max set solver suggests trying is where we inline at A and C. And at this point, the data log solver says, well, I've been able to prove assertion Q2 now. But there's still assertion Q1. But at this point, the max set solver says, I've finished searching through the entire space of abstractions, all 16 of them. And therefore, it is impossible to prove assertion Q1 in this abstract domain. Okay? There are several differences between our concept of cigar and traditional notions of cigar. I'll just mention one of them here. What we noticed here was that not only were we maximizing the generalization of failure within each iteration, as you just saw, but it was even happening across iterations at the level of constraint solving. So in the first iteration, for example, in the case of proving this particular assertion, showing that there's no path from node 1 to 3, we eliminated abstractions where A and C was set to 0, and in the third iteration where A and C was set to 1. But what the max set solver is looking at is the cumulative set of constraints that are accumulated over iterations. And so it can now even reason about counterexamples that are spliced together across iterations. So in particular here, it can reason that there's no point in trying an abstraction where we have A0 and C1. And this is what lets us accelerate the convergence of the cigar loop. Okay? So I'm going to show you some experimental results to demonstrate the effectiveness of this technique. So we implemented this using off-the-shelf solvers. So we did not make any modifications to either the data log solver or the max set solver, which means that you can use this technique with newer solvers as they get faster and better. Okay? And we applied these to 2 different analyses for Java bytecode programs that have been challenging to scale. One is a so-called k-object sensitive pointer analysis, which matches not only calls and returns, as I showed you here, but also heap, field, reads, and writes, up to a bounded depth. And the other is a type state analysis, which is similar to what tools like SLAM and so on are accustomed to proving, so temporal safety properties. And here's the number of rules and relations that are needed to handle the full Java bytecode. And we evaluated this on reasonably large Java programs, up to 500,000 lines of code. So I'm going to show you only the results for pointer analysis, because the others are similar. First of all, our approach needs a certain set of assertions or queries to begin with, because it is going to tailor the abstractions to proving those queries. So here's the number of queries that we have in each of these benchmarks that come from well-studied clients of pointer analysis. The baseline that we are using is a non-abstraction refinement approach. So it uses a uniform level of context and object sensitivity at all sites. And what we can see is this approach can only prove up to 50% of these queries, whereas our approach can resolve all of them. I'm also showing some statistics of how expensive the abstraction becomes in our approach. So the largest number of sites that we have is 58,000, which is similar to which is analogous to the 4 sites that I showed in the small example, which means that the search space is 2 to the power this number. Okay? But our approach ends up by inlining only a tiny fraction of these sites, okay, which is only less than 3% of these total number of sites. And here's the total number of cigar iterations. Now let me show you some statistics about the performance of this data log and maxset solver on a single benchmark, LU search, in our study. So what I'm showing you here is the different cigar iterations. And on this y-axis is how the abstraction size grows across cigar iterations. And here, the running time of the data log solver. And what you see here is the abstraction size is growing all the way from inlining 0 sites to 140 sites. Okay? But in each of these invocations of the data log solver, the running time remains fairly constant, which means that we are indeed hitting cheap abstractions. We are never using very expensive abstractions. Okay? In contrast, if you were to use uniform abstractions up to depths of 1, 2, 3, and 4 of inlining, then here's the performance of the data log solver. Okay. In fact, what we are achieving here is 10 levels of matching calls and returns and fields and writes. So it's up to k equal to 10, which is reasonably sufficient for fairly large Java programs that we are interested in. Okay. Now let's also look at the performance of the maxset solver. What happens here is there's an interesting trend, which is in the first half of iterations, the maxset instance gets harder and harder to solve because we are finding more and more ways to fail to prove certain assertions. And so it gets harder and harder for the maxset solver to suggest new abstractions that avoid all those failures. But after a while, certain assertions start getting to be proven, and others shown impossible to prove, and therefore the maxset solver's problem becomes less and less constrained. Okay? But nevertheless, we never go above a few seconds in solving these maxset instances. Now, these maxset instances are fairly large, going up to 24 million clauses and 7 million variables. Okay? So this will motivate the second part of my talk, where I will discuss new techniques we developed for solving very large maxset instances. Okay? But this is using an off-the-shelf maxset solver. So I talked about the first application. We used a similar methodology for the other 2 applications, but I'm not going to go over the entire maxset encoding this time. Okay? So let's look at alarm classification. So unlike automated verification, in the domain of bug finding, it is OK to have false negatives, but we still want high accuracy, which means we want few false positives and few false negatives. Okay? And typical bug finding tools today produce a lot of false alarms. In fact, here for a certain Java program, everything from R2 through R5 is a false alarm. Only R1 is a real alarm. And in this case, it's a data race, static data race detection tool for Java. So the question is, can we provide a minimal user interface here where a human could just say which reports he or she likes or dislikes, and then rerun the tool and get a generalization of the feedback. Okay, so not only are the reports that the user disliked eliminated, but also similar other reports or reports correlated to it also get eliminated. Okay. So, well, I can show you how to solve this using MaxSat. Let's look at an example underlying analysis that produced these reports in the first place. So I've shown you a few rules of the actual data race analysis that we have for Java. Okay. So here, for example, this relation encodes control flow graphs. Okay. So it has all pairs of program points P1, P2, such that P1 is an immediate successor of P2. Here is a relation that is produced by another software analysis, in particular pointer analysis, which says which pairs of program points may access the same memory location. And there are others, such as whether program points P1 and P2 are guarded by a common lock. So all of these are relations that we would need in order to accurately predict data races. As output, we are going to produce one intermediate relation which tells which pairs of program points may happen in parallel, and then the final relation which produces these bug reports, which is which pairs of statements may be involved in data races. Okay? So these constraints look fairly similar to the graph reachability example I showed, slightly more complex than that. What you see here is that if statements P1 and P2 may happen in parallel, and P3 is a successor of P1, then P3 and P2 also may happen in parallel. Here's the commutativity rule, which says that if P1 and P2 may happen in parallel, then P2 and P1 may also happen in parallel. And finally, we have the rule which produces the final bug reports, which says that there's a race between P1 and P2 if they may happen in parallel, and they may access the same memory location, and they're not guarded by a common lock. So this is the classic definition of a data race, of a lock set-based data race detector. Okay. But as you can see, these rules are incomplete, which is why they produce a lot of false alarms in the end. To give you a simple example of an imprecise rule, let's look at this particular rule. Here we have a case where, let us say, P1 is known to happen in parallel with some other program point P2. Okay, so this fact is true. P3 is indeed a successor of P1 in the control flow graph, but it cannot be the case that P3 and P2 may happen in parallel. And the reason is that because P3 is actually dead code. If you see here, this condition can never be true. And so there itself, we have a rule here which is sound but incomplete. Right? Since we are not after verification here, we can make this analysis itself probabilistic, and we can make this rule a soft rule. Okay? Remember the weight learning problem? So we can learn this weight from training data, from fully labeled data that we have collected in the past. Okay, so let's say it's a weight of 5 here. Certain rules we might want to keep hard for soundness reasons, right? Or for some other fundamental reasons, such as the commutativity property. And then we want to somehow encode the human's feedback on our bug reports, which here is indicated with a much larger weight. So you might wonder, why is the user's feedback itself also a soft constraint? Well, that is because the user might be wrong once in a while. And in any case, we don't want to over-constrain this problem and make it unsatisfiable. Okay? So let us now see this in action, how this resulting probabilistic analysis works on generalizing user feedback. So here what is happening is we indeed have a real data race R1 between these two accesses to the memory location request. But then these remaining 4 bug reports are all false. And the reason here is there's an atomic test and set synchronization idiom that our data race detector does not understand. And so it believes falsely that the function close can be called in parallel by 2 different threads. Okay. What we have here is, as before, the data log solver produces a derivation hypergraph. And when the user's feedback arrives here saying that he or she dislikes a certain bug report, in this case, the data race between accesses x1 and x2, and we rerun the MaxSat solver, what we see is a very interesting phenomenon in this part of the derivation graph. Okay? In particular, the MaxSat solver concludes that it is better for it to sacrifice this reward of 5, okay, by violating this particular instance of that rule. and thereby gaining the reward of 25. Okay? So in that process, the solver suppresses this particular bug report, which the user just disliked. But another thing that happens is the other bug report that we had here, which is a data race between y1 and y2 that is also false, gets eliminated. And the reason for that is I haven't shown you the rules that encode the least fixed point semantics. So the moment you cannot derive the fact that x1 and x2 may happen in parallel, you can no longer derive the other parallel tuples similarly. And therefore, all data races downstream also are suppressed. Okay? So this should just give you some intuition for how user feedback is being generalized. Okay, now let us look at the results on, again, very large Java programs using realistic software analyses. So what we did here was ran the following experiment. For each of these programs, we know the ground truth from labeled data that we have collected, that here there are 338 false positives and there are 700 true positives. Okay. We randomly decided to pick 5% of these reports, so a mix of true and false positives, and label them appropriately with likes or dislikes. So if they were false alarms, then we disliked them, and if they were true alarms, we liked them. Right? And then we reran our tool. And what you see here is fairly massive generalization. So for example, for the Aurora benchmark, after giving feedback on just 5% of these reports, almost 70% of the false positives go away, while retaining almost all 100% of the true positives. Of course, this is just bug finding. There are no formal guarantees at this point. Okay, and indeed, we have false negatives. If you see, not all of these bars are touching the 100% mark. So false negatives do creep in. Anyway, the high-level conclusion is with just 5% feedback, 70% of the false alarms on average are eliminated while retaining almost 96% of the true alarms. Okay? And this motivates a lot of future work. How do we, for example, use active learning to pick the right set of reports to give feedback on? In particular, we believe that even 1% feedback is enough if it is chosen in a smart way. Okay. Another interesting problem is how can we give statistical guarantees following ideas such as pack learning? Because we do have false negatives here that will be inevitable, but perhaps we can bound them in an interesting way. Okay? You might also wonder what happens as we give more and more feedback. So there's proportionate improvement as you give 10%, 15%, and 20% feedback, but it is not that impressive. Because remember, what is happening here is only the importance of the different weights in our constraint system is changing. In particular, the features that are needed for learning are not at all changing. The rules themselves have remained the same. And so another interesting future problem is instead of asking users to just give likes and dislikes, ask them for richer feedback, explaining why they dislike a certain alarm, which in turn translates into new rules at the level of our constraints. Okay? So this would be akin to learning new features for a classification problem. Okay? This goes under the structure learning problem that I alluded to earlier in the talk. Okay? I'm going to talk about the final application, which again has a very similar flavor. And this combines sort of the best of the previous two approaches, which is it brings the human back in the loop, but this time it gives the guarantees of soundness. So we call this interactive alarm resolution. Okay? So instead of making certain rules soft and giving up on soundness, we could instead just ask the human certain questions about intermediate facts. So in order to overcome the incompleteness of the underlying analysis. So for example, we could ask the human user, can this statement here on line 17 be executed by different threads in parallel? So notice that here the user is not looking at end reports, but is looking at intermediate facts. They could be loop invariants or other kinds of invariants that you're interested in. Now let us see what kinds of questions we can ask the user here. Well, we cannot ask questions about these facts because they are basic facts about the program. They encode the control flow graph. Okay? They can never be refuted by the human. Likewise, we cannot ask questions about end reports, because in that sense, it wouldn't be a very interesting way to resolve bug reports, right? If we are directly engaging the user and asking them questions about the alarms. That leaves us with the remaining interesting questions. So we can ask the user whether two threads may execute certain statements in parallel, or whether a pair of statements is guarded by a common lock, and so on. But again, because these graphs are very large, there's a rich space of possibilities. And even here, I can show you many different possibilities. But let's at least first get to what are our main objectives in asking questions. So the first is generalization. So we would like to ask far fewer questions than the number of alarms that get resolved, and thereby minimize the user effort. And the second is prioritization. If the user at any point wishes to walk away from interacting with our system, we want the user to have had the maximum payoff by then, okay? So now you can again see where we are headed towards a constraint optimization problem. What we see here is we have two reports, Rx and Ry, and I'm just going to show you some possibilities of questions that we can ask. So if we ask just one question, whether x1 may be executed in parallel by two different threads, which is this particular fact, then indeed we resolve both reports, Rx and Ry. So the user will say, no, this fact is false, which collapses this entire derivation graph, and so both reports are marked as false, in a sound way, provided we trust the user's responses. Okay? On the other hand, if we make the mistake of picking the wrong question, for example, if we ask whether y1 may happen in parallel to itself in a different thread, then we only eliminate report Ry, but not Rx. So we have wasted the user's effort here. Okay? And then if we ask questions such as whether y1 and y2 may alias, this in fact is true. So the user is not going to refute this fact, because y1 and y2 indeed access a memory location that is may aliased in the concrete semantics. Okay? So here the payoff is we have not resolved any alarms. So we have asked the user a question and not gotten any benefit. Okay? So I'm not going to show you the full maxat encoding here, but I'm just going to give you some highlights of what it looks like. So it should be evident by now that, first of all, this approach is iterative, very much like the cigar approach I showed you. In particular, we want to avoid asking the user to label all the questions upfront, because we don't know upfront what are going to be these labels, whether the user is going to confirm or refute them. And so if we have an iterative strategy, then that will overall help us ask the fewest possible questions. Okay? But on the other hand, within each iteration, we would like to maximize the expected payoff, which is we would like to get the most number of alarms resolved by asking the fewest number of questions. Now notice that this is a nonlinear optimization objective. Okay? So we have a division here where both of these are variables. And the reason we need to ask a set of questions in each iteration is, this goes back to how these derivations are encoded. There are both conjunctions and disjunctions there. So it is not optimal to just ask one question in each iteration. In general, you might want to ask a set of questions together. Okay? But the way we approach this problem is we simply do a binary search on the payoff by solving a sequence of maxat instances. And finally, it turns out that if you have no prior guess on what the labels might be, then this approach works really badly. Okay? So if it treats all user responses as equally likely to be confirmed or refuted, we end up asking a lot of wasted questions. But here's the good news. We can leverage a lot of unsound heuristics that people have developed over the past. We can take static heuristics. We can take dynamic heuristics, such as testing and likely invariants. We can even combine them using machine learning models, such as decision trees. And together, we can feed the results to a maxat solver to make the best decision. Okay? And using this, we get really good results when we combine all these heuristics. But notice that the unsoundness of these heuristics never affects the final result, because the maxat solver is only going to use them to prioritize certain questions and guess their likely answers from the user. So what we see here is, again, the static data race analysis example. notice that we end up asking the user a very small fraction of questions compared to the number of reports that the user would have to inspect otherwise. And in the process, we resolve almost all the false reports. Now, you might wonder, why are we not resolving 100% of the false alarms? Well, that is because at some point, the expected payoff becomes less than the payoff of just inspecting each alarm. There's only so much generalization and correlation and dependencies between these bug reports. Okay? So the punchline is, with only up to 5% questions to the users, 74% of the false alarms are resolved, with an average payoff of 12x per question. So if the user is willing to answer each of our questions, then on average, the user is saving inspecting 11 other reports. Okay. So that was the result for generalization. Let's see how well this does on prioritization. Okay. What I'm showing you in these red plots is the ideal case. We actually know what are the labels that the user is going to provide because we have Oracle data. We have fully labeled data. Okay. So if we were to feed that to a MaxSat solver, then it now knows the optimal case. And that is the red curve that you see. Okay. But the blue case is where our heuristics kick in. So they are not aware of how the user is going to respond, but they have some guess from various heuristics. So it is using a data-driven approach here. What you'll see is that in the initial iterations, which are the most important, where we'll get the maximum payoff, our heuristics do exactly as the ideal case, as the Oracle. Okay? So they predict the first few questions as well as if they had full knowledge of what the user is going to respond. Okay? For example, here in the case of the FTP benchmark, the very first 3 questions resolve 300 data race reports. But after a while, the two start to diverge because, of course, we cannot keep making perfect predictions, unlike the Oracle, which has fully labeled data. But at that point, it doesn't matter much anyway because the payoff is diminishing. So you see the cumulative number of alarms being resolved is tapering off. And at some point, our approach just stops asking more questions and tells the user it's better that you now just manually inspect the remaining alarms. Okay. So that was all about the 3 applications. I did not show the full MaxSat encoding for each of these, but we have provided it in the paper in the CAV proceedings. But here's a quick summary at a very high level. So there are hard rules as well as soft rules in each of these cases. In the first case for automated verification, the hard rules came from the analysis rules themselves, which was supposedly sound and encoding the logic of the analysis, but also from the family of abstractions that we provided for this abstraction refinement. The soft rules came from the relative costs of different abstractions and how much reward we want to give for resolving different queries. Okay. In the case of bug detection, we kept some of the analysis rules hard, which means we wanted them to be sound, but the others we made them soft, okay, which means we relaxed the soundness of these rules and allowed them to become probabilistic. And these reflect how much confidence the writer of these analyses has in those rules. And finally, we also made the user's feedback soft. What that means is how much confidence do we have in the labels that the user is providing. And finally, in the interactive verification application, because we want soundness, we kept all the rules hard. But now we assigned a weight dictating how much reward we want to give for resolving each alarm, and how much cost we want to charge for each question that we ask the user. And although I used a very simple cost model here, which is that the cost of inspecting each cause is the same as any other cause, and likewise that the cost of inspecting an alarm is the same as that of inspecting a cause. In practice, you can imagine a crowdsourced, data-driven approach where all of these weights are learned automatically over time to improve the user effort even further. Okay? There are also applications beyond software analysis that many of the techniques I'm going to talk about next are applicable to. I'm just mentioning 2 over here. There's the classic mathematical programming domain, but also a field of AI called statistical relational learning. Okay? So what I'm going to talk about in the next part of the talk is techniques that apply to all of these applications, whether in program reasoning or otherwise. But we'll especially take advantage of insights in our domain of software analysis, such as the prevalence of horn constraints. Okay? So we go to the second part, which is how can we develop scalable techniques for max-set solving. Okay, recall again that we are not actually solving a max-set instance. We are solving something at a higher level, which is a Markov logic network, right? And as a reminder, there are three things that we want from a solver. The first is we want soundness, which means that any solution that we get back has to satisfy all the hard constraints. The second is we want it to be optimal. What that means is the sum of the weights of the satisfiable soft constraints should be maximized. And finally, we want scalability, okay, which means we should be able to handle the very large instances that arise in our applications in practice. So you can look at solvers that have been developed in the past in various communities for this problem. So the databases community has looked at it for information retrieval problems. The AI community has looked at it for statistical relational learning. And even the PL community has solvers that are applicable here, such as Z3. But it turns out that none of them satisfies all the three criteria that we want. For example, the solvers from the AI community typically want to scale but do not give any soundness guarantees. In fact, they don't even have hard constraints typically. At the other extreme, you have solvers that do give soundness and optimality guarantees, but they don't scale very well. And to be fair to solvers like Z3, they are not quite handling the same logic that we are handling. So they are, for example, more expressive, and they use max SMT rather than max SAT. Okay? But nevertheless, if you were to encode our problems and feed them to Z3, it would not scale today. Okay? So we developed our own solver for scaling to these instances. And what I'm going to talk about is a very general framework that this solver follows. And I'm going to show two instances of this framework. Following the terminology in the data log community, I'm going to talk about bottom-up solving and top-down solving, and also talk about where each of these might be applicable. So the general framework for solving these MLNs is as follows. Recall that we have these two steps, grounding and solving, but we are not going to run them in those two phases because neither of them is going to scale. So instead, we are going to solve both of them in an iterative fashion. Okay? So we start with the MLN instance, but at any given point, we ground a very small set of constraints. Okay? We feed them to a max-set solver, so it is now able to scale, given that it's not given the full grounding. It produces a candidate solution that we then feed to a checker. And if the checker says we are done, despite looking at a small work set, then we have a soundness and optimality guarantees that we wanted. And if not, then the checker gives some counter examples that we then feed back to the max-set solver. So we grow the work set. And this process repeats. Now, as you can imagine, first of all, it provides all the three guarantees we were after. So when this loop terminates, you have soundness and optimality guarantees. And by its very nature, this whole loop is optimized to scale. Okay? So it handles scalability as well. But here's the catch. The checker has to be very smart and not unnecessarily grow the work set too much. And it itself has to be efficient in its check. And what we have done in devising this framework is not only developed new instances of this architecture, but also looked at existing solvers in the community and see how they fit into this architecture. And we have seen that others have used various technologies to do this check. You can use a data log solver or an SQL solver or an SMT solver or an integer linear programming solver and so on. In particular, if you use a data log solver for the checker, then what we get is the loop that I described earlier in this talk. Okay? If you recall, a max-set solver and a data log solver were operating in lockstep, where the data log solver was suggesting new constraints via derivations to the max-set solver. Okay? So it was effectively doing this check. Okay? The other one is bottom-up solving, where the check is done using SQL queries against a relational database. I'm going to go into more detail into this shortly. Okay. Yet another approach is to use a maxset solver for the check as well. And this goes to our work on top-down solving, which we call query-guided maximum satisfiability. Okay, so let us look at bottom-up solving next. So the main idea here goes back to an idea that comes very often starting from an integer linear programming called the cutting plane approach, which also lies at the heart of the cigar approach in the verification community. Okay, so I'm just going to call it the cutting plane method here. But we have adapted it with 3 insights for better scalability. So the first is, if you recall, we are not working at the level, at the propositional level of maxsat constraints. We are working at a higher level of Markov logic networks. And we are going to exploit this structure to efficiently find these new ground constraints. Okay, in particular, we are going to encode these MLN constraints as SQL queries, which can be executed very efficiently using a state-of-the-art relational database engine. The second is many of these constraints in our domain are Horn constraints. And so we are going to optimize for that as well. We are going to accelerate the convergence of this loop by using a data log solver, which is far more efficient at grounding Horn constraints. And finally, we are going to terminate this loop earlier by using a stronger termination check, where we only check for the objective value to saturate across successive iterations, rather than requiring the same set of violated soft constraints as in previous work. Okay? So I'm going to give you a sense of how this approach works by means of an example. So we'll once again look at the MLN that we started with. And I'm going to denote edge tuples using solid arrows and path tuples using these dotted arrows. So let us say I give you this input program to analyze, encoded as this edge relation. And the desired output is computing all valid paths in this graph. Okay? So you have paths of length 0, 1, and 2. Okay. So remember that this approach calls a maxset solver and an SQL engine in lockstep. Okay? So in the very first iteration, the maxset solver gets to see this input. So even though if you were to fully ground this formula and produce a very large maxset instance for a large input graph, remember that we are grounding a very small work set lazily. So initially, we have only the hard clauses which encode the input graph. And at that point, the maxset solver comes up with a solution which says, well, the path, that there are no paths in this graph, okay, because this is a valid solution. At that point, we feed each of these constraints in this MLN as a SQL query against an RDBMS, okay. What we come to know here is that this axiom is immediately violated by the current solution. Okay? We should at least have paths of length 0 for each node in this graph. And so in the next iteration, the maxset solver is seeing a larger work set, which is that there should at least be paths of length 0 for each of these nodes. At that point, the maxset solver gives this solution, okay, where it computes paths of length 1. At that point, we again feed each of these constraints to an SQL engine. This time, the first query passes, okay, because indeed we have all paths of length 0. But the other 2 SQL queries corresponding to these 2 constraints fail, because we have not yet derived paths of length greater than 0. Okay, so at this point, we ground more constraints. And now the maxset solver derives paths of length 1. But then we see more violations, and the work set grows, and the maxset solver then finally derives the right solution. And finally, when we again ask whether any of these queries is violated anymore, we get some more grounded constraints, but at that point, the loop terminates. Okay? Now, you might wonder why it took so long to compute this simple graph reachability solution. And indeed, if what you have is mostly Horn constraints, we are going to actually run a data log solver, which is going to eagerly ground these constraints. Okay? And so it will produce, in fact, the expected solution upfront. But then we will still resort to the same loop I showed before, except that this time it will terminate in just 2 iterations rather than 5. Okay? So let us look at how well this works in practice, again, on some of the large benchmarks that we have. So if you were to ground everything, okay, and feed this to a maxat instance, here's the size of constraints you're looking at. So this is the number of clauses in the maxat instances, okay? So we wouldn't even be able to store these in memory in a reasonable amount of time. Okay, so what this suggests is that we have to be lazy, okay, and use our iterative approach. Now, if you use the fully lazy approach, which has no knowledge of horn constraints, then it can take a long while for this loop to converge, right? But it does converge, and it does ground a small fraction, okay, up to 1.2 million of these 10 to the power 26 constraints, okay? So indeed, it is keeping the work set reasonably small. But if you use the optimization of horn constraints, then the number of iterations drops dramatically, and the running time is also much lower, but you might end up grounding a little bit more because this data log solver is a bit eager and might ground more constraints than the bare minimum, okay? So that was about bottom-up solving. Then we wondered about an analogous approach called top-down solving. And let me motivate it using an example. So in many domains, we are not interested in computing the entire solution. So for example, we are not interested in computing all paths in a graph, okay? The user might be interested in only certain paths. For example, in the program reasoning domain, the user might want to know whether two variables may alias on a certain line of code. This happens in other domains as well. So for example, in information retrieval, you might be interested only in knowing whether a certain author has authored a certain book, okay? And so this motivates the need for so-called queries at the level of maxat. So the original maxat problem only had one input. Now we allow another input, which is a set of queries that the user is interested in. And this induces this problem called QMaxSat, which simply says, given a maxat formula and a set of queries, come up with a partial solution, which is an assignment to just the query variables, but with the following completeness guarantee, that this partial solution can be extended to yield a complete solution that is optimal, okay? So for example, if a partial assignment here set A to true and D to false, we do know that there exists a completion of this partial assignment where we set B and C to true, such that this resulting assignment is an optimal solution of the original maxat instance, okay? But what we want to do is take advantage of this query that the user has provided and not unnecessarily ground the entire maxat formula and solve it, okay? So the key insight here is we are going to instantiate this solver architecture that I just showed you in a very different way to keep the work set tractable, okay? Let us look at a simple example. So let us say that we are interested in a singleton query, which is a Boolean variable v6, okay? And we have two kinds of clauses here, unit clauses and these disjunctions, which are implications. I'm going to denote them graphically as follows, okay? So the unit clauses are going to be nodes in this graph. And if it's a positive literal, then I'm going to denote it with a T. If it's a negative literal, I'm going to denote it with an F, as you see negated V7 here, okay? And then the remaining clauses, which are disjunctions, I'm going to denote them using edges. So for example, here we have V3 implies V1, okay? And all of these are soft clauses. So here's how our lazy approach works in the top-down setting. So because the user is only interested in the answer to V6, we have to at least, in our work set, keep clauses that refer to the variable V6, okay? So those are these four clauses, okay? You see V6 appearing exactly in these four clauses. At this point, we feed this work set to a maxat solver, and it comes back with a satisfying assignment, which is all of these variables, V4 through V8, set to false, which I'm going to denote in red. Okay? By setting all of these to false, I gain a reward of 20, which is the maximum possible reward, right? But we are not done yet. We have to ensure that we have a completeness guarantee. Okay. So in particular, what we need to do is see how this work set interacts with the rest of the maxset instance. And we call this the summary set or the frontier. Okay. So now this frontier here has the following highlighted clauses. In particular, if there's any clause that shares a variable with any clause in the work set, then that is part of the frontier. So you see here, for example, V4 is referred to in the work set over here. Likewise, V8 was referred to here, and so all of these are in the frontier. But notice that this particular clause is not in the frontier because neither V1 nor V3 are referred to by any clause in our work set. Okay? Once we get this frontier, the next thing we do is ask, were any of these clauses satisfied by just happenstance, right? And indeed, 2 of these were. Because we set V5 to false, so it is red, these 2 clauses were satisfied, coincidentally, but these 2 haven't been satisfied because both V4 and V8 have been set to false, okay? So at this point, we put these clauses into our summary set with the corresponding weights. And we ask the following check. So just like I showed you the solve part, now I'm showing you the check part. And notice that we are using a maxset solver for the check part, as opposed to a data log solver or a SQL engine. Okay. So here's the sufficient condition to terminate in a sound and optimal way. We have already computed the objective value of the current work set. We want to know whether by including the frontier that was not coincidentally satisfied, can we get a better objective value? If so, it means we are not done yet and we need to grow the work set. But otherwise, we are done and we have a guarantee that we don't need to look further in the maxset instance. Let us look at what happens here. So if you feed this formula to the maxset solver, it actually gives you a reward of 220, okay, as opposed to the current reward of just 20. And why is that? So this check fails, and that is because if you set all these 5 variables to true, then you gain the rewards of not only these 4 constraints, but also the reward of these 2. So you get a reward of 220. What that means is we now need to grow our work set. At this point, we have set the maxset solver sets all these variables to true, and we do a similar check again. But this time, something interesting happens. We are now looking at variables in these constraints in the frontier that are not at all referred to by any other constraints in the work set. And so if we compute this check, the maxset solver is going to trivially assign weights to these free variables, and thereby gain a higher reward, which will then force us to ground more and more. And so we do an over-approximation trick here, which is that whenever we notice any Boolean variables, such as V2 and V3 here in the frontier clauses, that were not referred to by any other clause, we are going to give them a pessimistic value. Because this is a disjunction with a positive literal V2, we are going to set both of V2 and V3 to false. Okay? And despite under this constraint, if a maxset solver cannot get a better reward, then we know that we are done. Okay? And so we have done this over-approximation step. At this point, it does happen to be the case that the maxset solver still can achieve a higher reward. And therefore, we are not quite done yet. This forces us to ground even more. And at this point, we again do our over-approximation trick. And finally, after grounding all of these clauses, after grounding all of these clauses except the one you see here, we have concluded that it is OK for V6 to be set to true in some optimal model. Okay? Now, notice that not only did we not ground this clause, but we did not ground any of the other clauses that you might have in this large formula. Okay? But there are no hard guarantees. This is just a heuristic. In the worst case, it could engulf the entire maxset instance by continuing to ground more and more. Okay? But it performs pretty well in practice. So what we did here was, if you recall, many of our applications had these queries to start with. Okay, we had queries coming from assertions or alarms that users were inspecting and so on. So we fed these queries here in each of these applications and converted them to the top-down setting. Okay? And we use this particular instantiation of our solver. Now, what you can see here is the total number of clauses and variables in each of these benchmarks to start with. So it is fairly large. But if we use our top-down approach, then we can solve all of these instances in a few seconds, as opposed to some baseline MaxSat solvers, which are the winners of these annual competitions, MaxSat competitions, that time out on most of these instances. We have, in fact, fed many of these instances back into the annual competition, and so they are now part of the future competitions. You will also see that existing MaxSat solvers have no choice but to inspect this full formula, and many of them crash on this input itself before actually trying to solve. Whereas our approach lazily grounds a smaller fraction of all these constraints. Okay? The memory usage is also fairly low compared to what it would be with a regular MaxSat solver. A last twist in our work on efficient techniques for solving is incremental solving. So what you might have noticed by now is this trend of solving a series of MaxSat instances in each of our applications. And typically, these instances add more hard and soft constraints. Okay? And so what we have done is we have made existing MaxSat solvers incremental in order to avoid solving each of these instances from scratch each time. So there are two levels of incrementality: the MaxSat level, where the application itself is solving a new instance, MaxSat instance that is growing. And so we can reuse the unsat cores from previous iterations. And we are looking at a particular kind of MaxSat solver, which is the most popular kind, the core-guided MaxSat solvers. But notice that the way a core-guided MaxSat solver works is by making a series of calls to a SAT solver. And so we can even incrementalize at the level of SAT solving. Okay? I'm not going to go into the algorithm we use for incremental MaxSat solving. It is described in this paper. But the key idea is that, to our surprise, neither of these two extremes worked well in practice. What I mean by that is the non-incremental approach nor the fully incremental approach. And we need something in between these two extremes, which we call sporadic restarts. So once in a while, we need the MaxSat solver to forget the history as new and new clauses are coming in. And we trace this problem back to what are called bad unsat cores, that if the MaxSat solver were given a fresh look after a while, then it would find higher quality cores. Now, how do you detect these bad unsat cores? We use a very simple heuristic, which is we ask how many times has a soft clause in the original instance been split. Okay? And splitting a soft clause is the way core-guided MaxSat solvers work. And we take it as a hint that if a soft clause is being split too many times, then it is likely time to restart afresh because the existing cores are unsat cores are of bad quality. Okay. I can show you some performance results here. So here are the classic cactus plots that you see for SAT and MaxSat solvers. We have solved 74 sequential MaxSat problems. So these are chains of MaxSat instances. So for a total of 669 MaxSat instances over these 74 sequences. And you can see that by going fully incremental without doing any restarts, the performance actually is very poor. Okay, so very quickly, the increasing number of new clauses prevents this incremental solver from taking a fresh look. And so a fully incremental approach does bad. The fully non-incremental approach is reasonable, okay? But the best approach is the one where we are in between these two extremes with occasional restarts, where the split limit is 5. So if you use too low a split limit, it's not good, and if you use too high a split limit, it's not good either. So we arrived at 5 by experimentation, okay? Now, while this might not look as impressive, we are only solving a few more sequential MaxSat instances over here. If you look at the individual maxad instances, you see a lot of improvement. So this particular line at 45 degrees compares the performance of the non-incremental approach, which is the best currently, against our incremental approach with the split limit as 5. And what you see here is many of these 669 individual maxad instances lie above this 45-degree line, which means that our incremental approach is doing better than the non-incremental one. And furthermore, this band you see is 10x speed up. So for many of these individual maxad instances, you are actually seeing close to 10x speed up. There's a lot more work, we believe, that can be done in incremental maxad solving. So in terms of future directions, we believe that there's a lot of advances that were done for Horn constraints in the data log community. For example, combining top-down and bottom-up solving using the so-called magic sets transformation, which optimally grounds constraints. It is an open problem how to do this for SAT and even more so for MaxSat. Okay, but that would be a great achievement if possible, where we would optimally ground constraints and unify the top-down and bottom-up approaches. The other is whether we can transfer the literature from SAT solving over to MaxSat solving. So the MaxSat competition started hardly 5 years ago, and so the problem is much newer compared to the SAT problem. And even problems such as incremental maxad solving are only getting solved relatively recently. So we were the first to propose the incremental maxad solving problem, whereas the incremental SAT solving problem has been around, I believe, for at least a decade. And so one can ask, how can we take more and more of the results from the incremental, from the SAT solving community over to the maxad community? And notice that we have just scratched the surface here. We can only incrementalize a particular kind of maxad solver, which is a core-guided one, and we can only do it for adding hard and soft constraints. Some of our applications remove certain constraints. And again, the SAT solving community has handled that well. And it would be interesting to see how to do that in the maxad setting. Okay, so I'm going to now conclude with some high-level future directions. So the first is we believe that this is an interesting future trend for software analysis in general, integrating a human in the loop. There's a lot of work on the two extremes of fully automated and fully manual. But what we have been trying to do in recent years is find a fine balance between these two extremes. I already showed two such applications. One was for alarm classification, and another was for alarm resolution. But there's a lot more interesting stuff to be done here. I alluded to active learning and many other problems earlier. The other is combining logic with probability. So the weights I showed you in our application, often they were costs, but sometimes they were also probabilities. So in particular, when we were making certain program analysis rules as soft, we were actually giving them a probabilistic interpretation. And I believe this is, again, an interesting trend that you also see in the AI and machine learning community, which is people have explored these two extremes, the fully logical world and the fully probabilistic or statistical world. And it would be interesting to see how to combine these two in interesting ways. We used a particular model called Markov logic networks, and we solved only the map inference problem there. But as I mentioned, there are many other probabilistic models out there. Markov logic networks have their own limitations that are widely known that other probabilistic models don't have, and so we are looking into those as well. On the front of optimization solvers, so there's been a lot of research on decision problems, especially in the data log and SAT communities. And there is increasingly work on more expressive theories, such as SMT. And as I just mentioned today, these have even extended to quantified, settings with weights, such as MaxSat. As I mentioned, Z3 even has max SMT now, which subsumes all of these logics that I showed here. We looked at Markov logic networks, which were as expressive as MaxSat, but less expressive, in fact, incomparable to max SMT. And going even further, we can look at artificial neural networks and so on. And as each of these logics is targeted, there's the question of, can inference and learning scale? And as we saw here, typically they don't for the scale of problems we are looking at, and so we have to devise our own new techniques, potentially leveraging domain insights. And finally, another interesting trend is data-driven approaches. So we have a lot of data, especially for program reasoning today, in the form of open source repositories. And we also have a lot of labels on bug reports, invariants, and so on, specifications, and so on. And it would be interesting to actually scale many of the techniques I've shown here to this setting. So to conclude, I'd like to mention 3 key takeaways. So the first is we came up with a new methodology for incorporating objectives into a dominant paradigm for software analysis called the constraint-based paradigm. We also defined a general framework to solve the resulting weighted constraints in a manner that is sound, optimal, and scalable. And finally, I showed the practical effectiveness of this overall framework for 3 dominant applications of software analysis, which are abstraction selection, alarm classification, and alarm resolution. So with that, I conclude, and thank you for your attention.
I guess I'll break the ice with a question. So the framework that you showed in the very beginning, you showed this abstraction approach and how you can optimize it using MaxSat. And then you said that you have applied this to different problems. Do you have like a general framework, like something like abstract interpretation that you can easily adapt to different abstract domains, or do you design your analysis from scratch every
great
single
question.
time?
I overlooked some parts of this. It is indeed a general framework where all the user has to do is provide the specification of the analysis in Datalog and provide the family of abstractions. Now here's the limitation. It is general in the sense that it works for arbitrary analyses expressed in Datalog, but Datalog itself is limited in various ways. So for example, how do you handle infinite abstract domains? So how do you handle widening or non-monotonic transfer functions, or abstract domains which are infinite but with a finite lattice height? So various researchers have extended Datalog to handle these. For example, to handle non-monotonicity issues, how do you combine negation and recursion in interesting ways? Or to handle infinite abstract domains, how do you allow on-the-fly value construction? So there are flavors of Datalog which are pushing the frontiers to handle a richer class of program analyses, but we are not there yet. Right now, what we can do is sort of the lightweight analyses you see, such as pointer analyses, information flow analysis, type state analysis, various concurrency and security analyses. So anything you can express in the fragment of Datalog that I showed here. Okay.
Okay. So different question about the approach that you proposed about the user feedback. So in using user feedback. So you showed one example where you said you started out with 1,000 reports and 300. Wait a second. Like I think 30% of them were false positives, and the rest were actually okay. And you said you asked the user to classify 5% of them.
Yes, yes.
That's still 50, right? I mean, do you think that users will be willing to go through that much effort?
Right, so it's a good point. So in the papers we have shown that you can, so as the number of reports gets larger, we have even shown what happens with 1%. So I believe when I showed 5% of probably 1,000, so you're right, that is 50. 5% of 1,000 is 50. 1% of 1,000 is 1. 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 Here's why we increased it to 5%. As we developed this technology, we did not work on picking the right, so the system does not proactively ask questions. It asks the user to label any alarms. And if you just randomly pick a very small set, then it's unlikely to be the best in terms of generalizing. So we have done studies where we pick many different random sets, and we do see certain golden sets which are very small and very high quality in that they generalize massively. But we haven't studied this data in great detail to understand why this happens. But if you were to randomly pick 1% of the feedback for this 1,000 reports, it's very unlikely that you will get this massive generalization. So you have to at least go up to 5%, so that most random trials give you that generalization. Now, if you were to look at 10,000 reports, we wouldn't look at 5% of the feedback, we would look at much smaller. So after a point, you don't need a lot of feedback. But that said, active learning, as I said, is the way to go ahead with this, which is to come up with a smarter way to ask these questions proactively to the user rather than ask them to label a random set of alarms. Okay, thank you.